Imagine a fire hose that suddenly fires a massive, high-velocity cannon blast of water. In offshore engineering, we call that a slug, an intermittent surge of liquid violently launching through a subsea flow line toward the platform, and that liquid arrives with terrifying force. Far below the seabed, reservoir fluids are trapped under millions of tons of earth, meaning they can rush up the wellbore and hit the surface at pressures up to 15,000 pounds per square inch. This animated breakdown shows what is actually inside that pipe. It is rarely pure oil. Instead, it is a volatile, untreated mixture of crude, explosive gas, corrosive saltwater, and abrasive sand. Offshore engineers are caught between two opposing physical forces. Outside the equipment, the heavy ocean column is constantly trying to crush the hardware inward. Inside the pipes, the explosive well stream is trying to blow everything outward. Grounded, authoritative. An offshore platform is a specialized industrial habitat, engineered specifically to contain and redirect these subterranean forces as they transition from the reservoir to the deck. If the well stream entered the main platform processing area unrestricted, it would destroy the facility. The first line of defense is a massive buffer vessel called a slug catcher, built to absorb the initial shock and trap those sudden surges of liquid. From there, the flurry enters the heavy armor of the platform, the process piping. Built to strict ASME B31.3 standards, these thick steel lines use color coding, like bright yellow for gas, so crews can immediately identify the pressurized forces moving inside. The fluid then reaches the core organ of the facility. This diagram shows a cross-section of a three-phase production separator. As the chaotic well stream enters, it strikes an inlet diverter baffle, immediately killing its momentum. Once the turbulence stops, gravity takes over. The lightest phase, the gas, rises to the top. The crude oil floats in the middle, while the densest phase, the heavy salt water, sinks to the bottom. Looking at this process flow diagram, you can see how engineers step down the pressure across multiple separator stages. Moving from the high-pressure vessel on the left to the lower-pressure vessel on the right forces dissolved gas to safely bubble out of the oil. By systematically dropping the pressure toward normal atmospheric levels, engineers strip away the volatile gas and turn an explosive mixture into stable, export-ready dead crude. But that pressure at the wellhead doesn't last. As oil is extracted, the reservoir rock slowly empties, and its natural pressure drops, like a deflating tire. Once the reservoir pressure falls below the flowing pressure required to reach the surface, the well dies. If left alone, up to 90% of the oil would remain permanently stranded underground. To extract the remaining oil, engineers have to launch a counterattack. They use a technique called enhanced oil recovery, artificially creating pressure from the surface to force the remaining fluids out. The most common method is water injection. Massive pumps take thousands of barrels of highly filtered seawater and force it down dedicated injection wells into the outer edges of the rock formation. The water acts like a massive hydraulic piston, physically pushing the remaining oil toward the production wells. A mature oil field relies heavily on these artificial inputs. Pumping water into the rock serves as a critical life support system, reviving a dying reservoir and extending its productive life for decades. The easiest reservoirs have already been tapped. Finding new fields requires drilling in deep water, descending thousands of feet down into total darkness, where the external hydrostatic pressure is lethal to humans. Saturation divers can only go so deep before reaching the physical limits of the human body. To go deeper, the industry developed work-class remotely operated vehicles, or ROVs. Controlled from ships miles above, these unmanned submersibles use robotic manipulator arms and specialized tooling skids to assemble multi-ton wellheads directly on the ocean floor. And now, engineers are pushing the technology even further. Here is an isometric drawing of a subsea separation module. Instead of bringing the raw well stream up to the platform, massive separators and multi-phase pumps are installed directly on the seabed. By doing the separation right at the wellhead, heavy salt water can be separated and safely re-injected into the rock immediately. The platform pumps never waste energy lifting thousands of tons of water miles up to the surface. Moving the processing hardware to the seafloor neutralizes the disadvantage of deep water. Engineers bypass the limitations of the surface entirely, fighting the weight of the ocean on its own turf. Step back and look at an offshore installation in its entirety. It operates as an integrated pressure management ecosystem. Crews fight a continuous war on 3 fronts: holding back gas on the steel decks, injecting heavy water deep underground to sustain the reservoir, and deploying robotics into the crushing abyss. When systems overload, the flare stack serves as a safety valve, burning off unpredictable pressure surges to prevent mechanical failure. Offshore engineers transform these violent natural gradients into a controlled industrial stream, harnessing pressure to sustain the global energy supply.